Another application of circular motion is planetary motion. To understand planetary motion, first we need to understand the force acting on planetary objects. Let's look at a case of the Earth and the Moon. We know the Moon orbits the Earth. The orbital path is nearly circular. So why does the Moon stay near the Earth? Well, the Earth pulls on the Moon, just like it pulls on me and you. And there's a gravitational force on the Moon. But due to Newton's third law, there's a force on the Earth due to the Moon. Those forces obey Newton's third law, which is that the force on one object is equal and opposite to the force on a second object. Often these are called action-reaction pairs. So in the case of our planetary or large objects, what is this force and how do we calculate it? So in thinking about the force, we should consider the masses. Now, a bigger massed object would pull with a greater force on another object. So this force is directly related to the mass of the object. And because the force is equal but opposite, that means that if I increase the mass of one object, the force would increase. If I increase the mass of the second object, then the force would also increase. So it's a force that depends on the product of the mass. But as the objects are further and further away from each other, the force gets smaller and smaller. So there's an inverse relationship between the force and the distance between the two bodies, which we're going to call r. And it actually is a inverse relationship with r squared. So if we were to graph force versus position, we would get a function that looks like this. So like a 1 over r squared proportionality with our force. Now, just like most other things in physics, there's also a constant, and we're going to call it a big capital G. The big capital G represents Newton's gravitational constant. The gravitational constant has a value of 6.67 times 10 to the negative 11. Now that's not a constant that you would have to memorize, just one you have to know how to use. Now let's look at an example. What is the gravitational force between a 100 kilogram mass and a 500 kilogram mass when they are a distance of 2 meters apart? So we start with our gravitational force expression, substituting in the values for G, M, and R, we get a force of 2.08 times 10 to the negative 7, and that would be in newtons, as any other force is measured in newtons. And notice how small this force is, times 10 to the negative 7. That means that there are 6 zeros in front of the 2 before the decimal point. So this is a very, very small force between these relatively large objects. To us, a 100 kilogram object and a 500 kilogram object are not small. However, this gives us perspective because the gravitational force is a very small and weak force comparatively. But the bigger the mass, like the Earth and the Moon, the bigger the force, and it will be big enough to keep the object in orbit. Now that we know how to calculate the gravitational force, let's see how the gravitational force between two bodies provides the force needed to keep objects in orbit, like the Moon around the Earth or the Earth around the Sun. So the Earth pulls on the Moon, and that pull is a gravitational force, and it is directed towards the center of the circular path that the moon makes around the Earth. So this means that this gravitational force is pointing towards the center, and it is the only force acting on the moon because it's in space and nothing else is touching it or pushing on it. And so that gravitational force is pointing towards the center, and it's unbalanced. There's no other force acting on it. So the gravitational force is center seeking. So our gravitational force, which is G m over r squared, would be equal to m times v squared over r. Now for the moon orbiting around the Earth, or any kind of object orbiting around a planet, the r of the orbit is the same as the r for the circular path that the moon is making. Additionally, the mass here, which is the mass of the object that is orbiting, is equal to the mass of the object that the force is acting on. So we can do some algebra here and simplify the problem. Dividing by m on both sides allows us to cancel it out. Multiplying by r on both sides allows us to an r from both sides. This leaves us with G m over r is equal to v squared. I can take the square root of both sides. We can take the square root of both sides here, and that would give us the square root of G m over r is equal to v. This velocity is known as the orbital speed. R represents the distance between the two bodies, and m represents the mass of the object that is being orbited. Now the object that goes around in a circle travels the circumference. So the moon even travels a circumference or a distance. So if the speed is distance over time, and the distance is the circumference, 2 pi r, and the time for one complete orbit is the period, then I can set this orbital speed equal to the speed of an object moving around in a circle. When I do that, I will have that 2 pi r over period is equal to the square root of gm over r. Now if I square both sides, I can then solve for t, the period. So now I have that 4 pi squared r squared times r divided by gm is equal to the period. Remember, the period is the time it takes for the object to go around in one complete revolution. Now r squared times r is r cubed. Final step would be to take the square root of both sides, and when I do that, that will leave me that the period is equal to the square root of 4 pi squared r cubed over gm. Again, the r represents the distance between the two bodies. M is the mass of the thing being orbited. So the Earth is being orbited by the moon. So the mass of the Earth would be the m we would need to substitute. And capital T is the period, or the time for one revolution.